All right, so thank you everybody for coming to this talk, A Type by Any Other Name. I know there's a lot of other really fantastic presentations going on right now, so really appreciate all of you coming here and taking a listen to what I have to say. So with that in mind, hi there, I'm John. I'm a software engineer on Google's Abseil team. If you saw Titus's keynote speech yesterday, you'll know Abseil is an open source collection of all of Google's common C++ library code. And we've been working on that for a long time. This talk is more or less a lot of battle stories around making that happen. We had to do a lot of code reorganization, code moving around to do that. With that underway, we're going to be talking about refactoring. Hooray! Hooray! Seriously, though, here's what we're going to do. I'm going to talk about what I mean by renaming types. And talk about why you would even care about such a thing. Why is renaming types something that is like cool enough and worth enough of mention to have an hour-long talk at CppCon? A lot of examples. These examples are going to start to build up a list of things that user code can do, which can break other users at a distance, library maintainers or people who depend on them when people want to reorganize code and do these kinds of refactoring. And then we'll wrap it up. Great. So renaming types. What do I mean by renaming types? It looks like this. We've got a class. It's called old, a function that takes it. And we have some other code that's using this type. And we want everywhere that it says old to now say new. If you have a very small, just a little app, a couple thousand lines of code, if everything's self-contained, if you have control over everything in your code base, this is not hard. This is a very easy problem. You can probably just do a sed replace or something similar and you're fine. The key that we're going to talk about in this talk is that there's a sort of invisible line in the sand where at the top we have some common library code and at the bottom we have some user code in a leaf part of the application. And you can't expect in general that the people who are writing this business logic leaf application have knowledge or ability to make changes to the library code. And furthermore, you can't expect the library code to know who's using it. And this this creates more of a challenge when you're talking about a refactoring task, when you're talking about making substantive changes. This now becomes something that you have to deal with. You can't just go and do everybody at once. So why would we even want to rename a type? We're just changing a name. Is that a big deal? I think it is. You might want to do a lot of things. All of these up here are kind of dancing around the idea that a name has meaning. A name refers to a bunch of data and a bunch of behaviors. So when you refer to a name, you're implicitly referring to everything that type could possibly do or you could do with that type. And by changing a name, you can gradually change the meaning of your code in a better way. So you might want to upgrade. Maybe you have some old version of an upcoming standard type. Maybe you have an optional type in your code. I'm sure a lot of people here have some kind of optional in their code base. And they might want to move to std optional or Abseil optional. So you may want to upgrade. You may want to gradually rename everything that says my optional to std optional. You might want to move it. You might have maybe someone in your company wrote some really great networking code over here. And a lot of other people want to use it, but we don't want a bunch of people depending on leaf application code. That's not a good overall system architecture, system design. So we want to take this and put it in a central common location where everybody can get to it a little bit more easily. You might also want to fix dependency issues. This was actually a problem we solved in Abseil, where we had a problem dependency where a lot of our foundational code that you'll see in base couldn't use our good string manipulation libraries because it depended on base. So we used these sorts of migration tactics that I'll talk about in this talk to invert that dependency and mean that our foundational stuff can rely on more sane string manipulation instead of going down to C standard library string stuff or rolling their own string algorithms. That's no fun. No one wants to do it. But this bottom one's what I really want to talk about, to allow non-atomic code-based refactoring. And what I mean by non-atomic is the typical model we'll often talk about with refactors is maybe you have an IDE, you click the rename button, you click some button, and it generates some big change that does the refactor you want to do, and then you check it in. And if you're able to do that, like great, you don't need to do non-atomic refactoring. If that works for you, perfect, it's a lot easier. But often, non-atomic refactoring, taking this large change and structuring it in a way that you can make the change piece by piece by piece in smaller, more self-contained chunks, is a much more sane way of actually executing these kinds of large reorganizations and refactorings of code bases. Why do it? Why? What are the reasons we would actually do a non-atomic code base refactor? Your change may be too large to merge. This is a common problem that we have in Abseil. At Google, we have 250 million lines and growing every day of C++ code. There's double-digit thousands of developers adding code to this code base every day. And we like to do things like rename a type that's used 100,000 times all over that code base. And so if we tried to check in this change all at once, the time that it takes our version control system to actually turn all the bits and do the change, there'll be merge conflicts. It's literally impossible. Even if you aren't that large, it still might be an annoying game of whack-a-mole of, well, okay, I got to fix this merge conflict over here. Oh, wait, but then that code over there, and then that file got deleted, so now you have to figure that one out, and you just keep constantly having to put out fires and find the right time where you can just slip in that change in between your other developers who are trying to work. You don't really want to like revoke everyone's access to the source tree to do this. That's not cool. Let's not keep other people from working. They may also involve excessive coordination, right? If you want to make a change that goes maybe over like a front-end to server boundary or some kind of boundary in your code such that it's really hard to do it all at once. You might need to have a couple people have like 2 changes or 3 changes and they all go at the same time. This is something we have to do common, or make something happen one right after the other, just because of some code organization issue. They also introduce extra complexity. You take all of the risk of every single change when you make a large change, and this is more of a like just general engineering thing. Maybe a lot of your refactorings are, a lot of the part of this refactor is easy. All this stuff is easy, but there's some hairy stuff over here. And if you bundle them all into one large change, these little changes over here that are easy inherit the risk of this squirrely difficult change over here. So you're just making it harder for yourself. Also, like say you're, I don't know, an open source library repository. I don't know why anybody would do that. You don't know who's depending on you, necessarily. And even if you did, if you wanted to refactor something, you literally just, you can't make a change to all of them at once because they're all different repositories. So you have to structure your refactoring in a way that allows these things to be changed one at a time. Great, so the analogy I like to use is to fix a bridge, just build a second bridge, and then divert all the traffic to that bridge, and then get rid of the first one. There's some constant factor that building new bridges is cheaper in software than it is in hardware. Great, so there's a really easy question to come out of this. Why not just make a new thing? Why not make a v2 of our type? This is totally fine, and it's kind of orthogonal to the point that we're talking about. A lot of what we're going to do is make a new type. We're going to see a couple instances of these refactorings where we do make a new thing and migrate people. But the point is, there's no coupling between old and new. We want to try and create some migration path between old and new, and we don't want to have to do it in massive chunks. We want to be able to do it a little bit at a time. So a lot of times, maybe you just throw a v2 over the wall. If you don't have a lot of users, that's easy. But we're talking about larger situations, more core-like common code that might typically be thought of as almost unchangeable, and we want to provide a migration path for it. Here's one way to do it. You could have the 2 types convert back and forth to each other. Here we have an implicit constructor on new. It can implicitly converts from old, and it converts to new via operator old. We actually do this sometimes in Abseil. We have an int128 type that converts to all the other ints because that's what ints do. They copy and convert, whatever. But if this is a more expensive type, say you need to allocate in this constructor, or new and old are just big, they have a lot, this gets really expensive really fast when you're passing things back and forth. And it's not exact equivalence. We aren't just doing a rename. We're making a new thing and kind of making them play together. And here's what I mean. This code is problematic. You can't just migrate G to use vector new, because even though old and new convert to each other, we don't have that kind of covariance relationship where vector old and vector new convert. So you'd have to copy all the news to old, pass them in, do all your stuff, and then copy them back to news when you're returning them, or if you're doing something else with them, and you just have all of these spurious copies all everywhere, and it's just a big pain. It's a giant pain. It's not what you want. But we do have a tool to do what we do, to do what we want to do, and this is what I'm going to be talking about a lot for the rest of this talk, which is aliases. People use aliases a lot. They're typically used to just give things new shiny names. I'm going to try and convince you that aliases are a lot more powerful for software engineering over time than that. They're literally the same type. In this instance, old actually just doesn't exist in the type system. And I think everybody there has experienced this when you've had some kind of compile breakage that has to do with stood string, and the compiler doesn't give you out a nice, this isn't a stood string. It says, oh, this isn't a stood basic string of char, and stood char traits of char, and stood allocator of char. What are you talking about? And of course, if you have a template that's got a lot of strings, and all of a sudden you've got like 50 million lines of code that's all complete, and you don't know what it is because all those aliases, all the sugar's been removed. They're literally the same. So now this example is totally fine. We've decoupled f and g. We can change one without the other, without changing the other, because vector of old and vector of new are now exactly the same thing. One's just a different name for the other one. Great. So the analogy I like to use is this. With variables, when you make a reference to another variable, the reference and the original name refer to the same data. They're fundamentally the same in an interesting way. Whereas if you make a copy, as on the right, you have two things that are equal but not the same. They don't have the same identity. And similarly, aliasing, when you alias types, they're the same type. Just two names for the same thing, not two types that convert to each other. If there are any math-minded people in the room, this is also kind of like conversion of two types that convert to each other is kind of like two groups that are isomorphic. You still need to do a little bit of work to go from one to the other, as opposed to two groups or two sets or whatever that are fundamentally the same thing. There's a little bit of a difference between isomorphism and equality. So it's kind of like that. Great, so let's find some code. Let's do some real stuff, right? Just kidding, we're not at examples just yet. There's a little bit more we have to do. And I'm gonna talk about like a little hairy, some would call like expert-only feature of the language. So take a deep breath. We're going to breathe in and breathe out. We're all relaxed. Good. Are you relaxed? Awesome. Great. So we're going to talk about ADL. So here's the situation. We have a type called class, and we have a function which takes a class named very creatively. Every type, when you're looking at class, has associated namespaces to it in C++. What are the associated namespaces for class? Someone shout it out. N and the global namespace. The global namespace is also an associated type for this, which is going to be important later. It's going to be important later. But the point is that takes class is in an associated namespace to class, namely N. So when we have user code like this, they can just call takes class without actually qualifying it. ADL only works on unqualified calls, and what will happen is when the compiler searches for the function, it will look in all of the namespaces surrounding f for takes class. It'll also look at all of the associated namespace of every type which is passed to f and search in there. So it finds in class's associated namespace, it finds take class and calls it. Great. There are interfaces that are designed to use with ADL. Swap is the canonical example. Here's how you call swap generically. You bring swap into lookup by using stood swap and then call it undefined to trigger ADL. And this gives you a sort of extension point. You can write swap for your own types when just doing the 3-move thing that the compiler does isn't what you want. So swap, big swap of int would call stood swap. There are no other overloads. And swap of n : class calls the R overload n : swap. That might do something interesting. I think probably a lot of you in here have seen this, but it's good to go over because it's going to be important. So the takeaway from this is that ADL couples types and functions. It creates a fundamental coupling in the language such that when you're talking about types, talking about refactoring types, and specifically talking about the names of types, you can't ignore functions. They are tied together inextricably, so you have to talk about them together. That's one of the reasons that I'm looking at functions that take these types of refactoring. We're going to see that come back a lot. All right, breathe out. We've got a nice cute kitten. We're done with ADL, so here we are. Meow. Now we have examples. I'm not kidding with you this time. We actually have some examples. This is what we're doing. So here's a basic example. We've seen this before. This is what I had up. And what our basic strategy is we take the class new. We will change everything in that class definition to say new, where it says old, all your constructor names and all of that stuff. And then you alias, you create the old name turns into an alias into the class. This case I will give is not at all interesting. Like this is like kind of silly if they're just in the global namespace or whatever. This isn't that big of a deal. But this is more interesting and a lot more realistic. You have something in an old namespace. This is the situation I maybe was talking about where there's some leaf code over here that wrote some great utility, and you want to bring it into a common area. You also want to bring it into some kind of common namespace because that's a good way to organize your code. And we have some user code, and remember, we can't change these at the same time. This is a fundamental restriction of our problem set. This is our constraint we're trying to work around. Afterwards, we just put the class and the function in namespace absale, alias into it, and this situation works totally fine. This is great. Does anybody know what happens if that was the user code? Does this compile? Don't all answer at once. You have a 50% chance. You don't count. This does compile. This is totally fine. Aliases, if you remember, they're not in the type system. An alias is not a type. It's another name for a type. So the associated namespace of class and f is still absale, even though it's declared as an old : class in our function. And we've also moved f into namespace absale. So in this instance, both of the type and the function is in the type's associated namespace. The compiler finds the function via ADL. It calls it everything's fantastic. However, we have a different situation now. Often, one of the things you want to do when you're doing a large code base change, when you're doing a refactor, is you have some really old, crufty stuff you don't want to maintain anymore. Who here has things they don't want to have to maintain anymore in their code base? Yeah, that's what I thought. So for the record on YouTube, everybody raised their hand. So we have this old, crufty thing, f, that we don't want to have to deal with anymore. And so we don't want to bless it by moving it into the new namespace. We want to leave it over there. It's a signal for people that, hey, this is probably not what you want to be using. It's not in our core util namespace or whatever you want to call it. Use this thing over here. We don't want to migrate it. We don't want to deal with it. We want to get people off of it. Now what happens with this user code? Does anybody want to tell me if this compiles or not? Does G compile? There are a couple of people shaking their head. It does not compile. This is the error message from Clang 5. No matching function call for f. We can see f. It's right there. There's the matching function call, but it's not in an associated namespace anymore, even though class foo is declared as an old : class. Its associated namespace is absale, not old. So this breaks. This user, and this is an important moment, because the user has created a spooky action at a distance for the library maintainer they're depending on. Their life has gotten worse because they made their library maintainers worse. The whole point of having this library is that most of the Leaf application code, they don't want to write that library code. You don't want to have to deal with it. It does a thing, it has a contract, it does something I want to do. I don't want to have to deal with writing it a bunch of times. I don't want to have to deal with figuring that out. We want it just in one place. Here's where our logic is bundled. But by using ADL, they've created a coupling between the name that they're supposed to use for the type and where the type actually lives. It's completely reasonable, for example, for class to be an alias into an internal implementation type. That's completely reasonable. If you look at, I believe stirsplit does this in absale, where it does this magic splitting. It'll split a string into any container you want, and it returns an internal type that you're not supposed to name that does all these magic conversions for you. But the library author, people who are working on common.h, they have no way of knowing that you're calling them via ADL. So they've been broken by a spooky action at a distance that they weren't aware of. And this is going to slow down the refactor. This is going to slow down the maintenance of the core parts of the code base because the interface, this function f was called in a way that was not my words are failing me. It wasn't expected. So we're going to bring up this list now. This is a list we're going to build of ways that user code can make the lives of library maintainers challenging. Or I like to call it, how to make a puppy sad. How can you make this poor little pupper sad? Call code you don't own via ADL. And there's 3 parts to this, and 2 of them are interesting. It's the fact that you don't own the code, and you called it via ADL. And this idea of code ownership is really important here. The Leaf user code, these are not the experts in maintaining the library code, nor is their time prioritized to work on the user code. They're off making some cool application. They're off making something happen. They don't want to be prioritizing time to maintaining their building blocks. They don't have to. So unless this library is designed, like swap, to be called via ADL, there's not a particularly good reason to call it via ADL except saving a couple keystrokes, as far as I'm aware. So this is an example of what we at Google like to call Hirams Law. It's an observable behavior of the type. People depended on it. At a certain as the number of users n grows to infinity, the odds that somebody is depending on every observable behavior of a type or function, even if it's not part of the explicit interface of it, goes to 1. It's going to happen. Also, just if you use the global namespace, you're going to make the puppy sad. You're basically forcing every call to maybe use ADL, because who here likes to write : size t? Does anybody actually fully qualify anything in the global namespace? Yeah, who goes : stir comp? No one writes that, even if you're writing stir comp. So you have the opportunity to unwittingly trigger ADL if that type moves underneath your feet. The whole idea, again, is separating the concerns of user code and library maintainer code. So here's another example. Now we're changing a name and a namespace. And this is subtly different and introduces some other problems. And I want to look at the 2 different using statements in namespace old. One is an alias. Using old equals absil new. We're actually making a new type. This other thing is not actually an alias. It's more of directions to the compiler. It's a using declaration, I think, is the name of it. It's a little bit different, although it's similar enough for our purposes. That's why I've just been calling them aliases. But this is a completely separate thing, and it'll get worse later. This code compiles. This is totally fine. But what if a user did something clever like this? People forward declare types all the time. It's something a lot of people want to do. Maybe they don't want to increase code bloat by including a header because you're only referring to this thing via a reference or a pointer. Maybe you want to decrease your binary size. Maybe this is going to help your linker some way. This is something that people do all the time. But we're confusing the compiler here. The user over here is saying, yeah, old is a class or struct. Actually, I think if old is declared as a struct, this still works. The old is a class type compiler. But the library maintainer, who's actually in charge of it, says, no. Old is a type alias. Old isn't a type at all. It's not a class. It's not a type. It's just another name for absil new. And indeed, we get this compiler error. Definition of type old conflicts with type alias of the same name. So this is another instance of an implicit interface that wasn't meant to be exposed, but is exposed just via the mechanics of the language. The language lets you do this. And if you control everything, or this is a short-lived project, go ahead and forward declaring doesn't hurt anybody. If this is your own class that you control, it doesn't hurt anybody. It's only when we're passing over a barrier of who owns what that now you're creating additional burdens on other people who are the actual owners of the code and not you. So, as it turns out, pandas are made sad by everything that you can make sad with a puppy, but you can make pandas even more sad than puppies. You can make pandas even more sad than puppies. Forward declaring a type you don't own will make pandas sad. I just talked about why this might be a bad idea. Also, opening a namespace you don't own makes pandas really, really sad. This is basically the same rule as don't open namespace std. There's a reason it's in the language. It's in the language spec. If you open a namespace that you don't own and put any name in it, then you basically void every possible guarantee that your library maintainer could make about the code, because they don't know what might be a name collision. And this is even more sinister, because maybe your code that's like in the middle, maybe you're not leaf code. You have some people depending on you over here, and you're also depending on this library over here. Maybe you're depending on one half of this library, and you add a name to it. You open namespace absel or std or whatever, and write your own symbol into it, which happens to be present or made present in another part of the library you're not including, so it just happens to work. There's no ODR violation. Until someone includes you and also that thing, and now you have two definitions for the same symbol, the library maintainer had no way of knowing that you stole a name from their namespace, and now there's an ODR violation for these guys down here for nothing that they did wrong. They just wanted to include two things, but you've introduced an artificial coupling in the dependency graph of the program. Again, this is all based on the idea of code ownership and not crossing that code ownership boundary. When you cross the ownership boundary, being a little bit more principled about how you're using code that you don't own. Oh God. What about templates? Yeah, whatever. You can alias with templates exactly the same way, exactly with the natural syntax that you would think. This does exactly what you think it does. But I do want to make one point. You can do a using declaration, and then you don't need to do the templates. The template introducer. This is a much simpler case. And what I mean is, these are often called metafunctions. And what I mean by metafunction is if you squint really closely at old, you can look at it as a function from a type to another type, new of t. It doesn't return a new of t, it returns the type new of t. And as we're all aware, you can do arbitrary calculations in the type system of C++. So template aliases are an extraordinarily powerful tool, and just like any other extraordinarily powerful tool in C++, with great power comes great responsibility and great ability to shoot off your own foot. So here's a rename of a template. I'm cheating. This is actually a function. You could imagine this happening with the type 2, but this is something that happened to absel. If you replace f with make unique, this was a situation where a user had a struct or class, and their constructors were private, but they wanted to use make unique. So they friended it. And make unique, if you look at absel right now, it's under absel memory, it returns an internal type. It returns a type in absel : internal. But to make this friend declaration, they had to name that type. They had to name the signature of the function. So this worked. This worked for them. It compiled, it ran, and did what they thought it would do, until we moved it into namespace absel. And now, old : internal doesn't exist anymore. It's gone. And that name internal should have been maybe a warning sign that perhaps this is subject to change. And indeed, no member named internal in namespace old. So you can make owls really sad. Look at him. If you name an internal type you don't own, you will make this owl very, very sad. It says internal for a reason. The whole point of depending on a library is so that you get to ignore these internal things. Like, this is the stuff that you don't have to worry about. You don't care. It's not your problem. That's why it's in a little library code, and it only needs to be touched when that thing needs to be maintained, instead of every time somebody wants this kind of functionality. As a related thing, specifying deducible type parameters is also often a problem. This is our issue with make unique. If you have a function with a template parameter that can be deduced, there's nothing saying that unless it is specifically specified, like by template functions in the standard, which do specify the meaning of their template parameters, there's nothing saying that the template parameters of a function couldn't change meaning to make an easier implementation. Maybe it makes the metaprogramming easier. Maybe they upgraded to 17 and now they can do something cool with fold expressions and type packs they couldn't do, or something like that. This couples to the implementation. Now, owls are very, very wise animals, supposedly. So this sad owl is able to sum these up in a really nice phrase that is pretty common engineering knowledge, in which I've said a lot, but bears repeating with the additional knives that C++ gives us, with the additional everything that C++ allows you to theoretically do in code. Don't rely on implementation details of code you don't own. And this bears extra repeating in C++ because the details that you could rely on in C++ are there and they're easily accessible. It's very, very, very easy to just say, blah, 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 : internal. We don't have types that are private to a module like other programming languages do. We don't have the ability to hide things as well as other programming languages do. Sometimes build systems can get around this. Bazel, Abseil's build system has visibility rules that can kind of help us out a little bit here, but if these are named in a header because you're doing template code, all bets are off. So just because it's possible to rely on implicit interfaces of a type doesn't mean that it's a good idea over time, or in a situation where you're affecting that guy down the hall's code and making life difficult for him when all he wants to do is help you. He's trying to be your friend, just trying to be your friend. Got one more example. Oh yeah, now we have a happy owl, look at him. You didn't rely on internal implementations. Look at him, he's so happy. Dependent types, I got one more thing to talk about. I've got a little story to tell. We got to talk about dependent types. There's no scream this time, although maybe there should be. A dependent type is a template type, and it is dependent in the sense that the actual concrete instantiated type depends on the template parameter. And what this means is that, so for example, this is remove const. This is a pretty simple one from the standard library. It does exactly what it says on the tin, it removes const. But you could imagine that this is a more complicated type where maybe remove const of int type is actually a static int. The type is just an idiom. It doesn't actually have to be a type. There's no way for the compiler to actually know necessarily what this is statically. You also can't get away from it. You can't hide. Remove const underscore t is just an alias for remove const of t : type. But dependentness of a type is viral. You can't hide it. It's dependent all the way down. And here's the point I'm making. Template parameters of dependent types can't be deduced. If you have a function, or I guess now a class in C++ 17, although I have to admit I'm not that particularly familiar with constructor template parameter deduction in C++ 17. If you have a dependent type in the argument list, the template parameter of that type can't be deduced. That template type has to appear again somewhere that the compiler can figure out what it is and then insert it back to that template parameter and say, oh, t and t here must be the same. And maybe I have a, I don't know, remove const t and then an int, and then a t, and then t is passed as int, and then, oh, well, this must also be int or something. But you can't ask the compiler to actually deduce these. And if you squint really, really closely and think about how the type system is Turing complete, asking the compiler to deduce template parameters of dependent types starts to look a little bit like a halting problem. So now here's a little story. And this is going to be a last little story about a battle story I had in Abseil. Merging types. Why do this? Why would you take two types and make them one, or three types, or n types and make them one? It turns out there's a lot of interesting things you can do with this. It's very often that disparate parts of a code base will write kind of the same thing in a lot of different places with kind of the same semantics, but just different ways of spelling the same thing. You can write one central type in your central location, create the thing that's going to exist after you clean them up, and then internally shovel off to different implementations and then just fix these guys over here and these guys over here and these guys over here instead of having to do a bunch of wholesale migrations. And the first two bullet points are the kind of same thing. You can also abstract away semantic differences. There's another talk going on right now about how at Google we're replacing approximately every occurrence of unordered map with our own hand-rolled map and saving just gobs of memory and space. And when it's on YouTube, you should all watch it. It's a fantastic talk. We didn't do it this way, but it was discussed having the new map type initially be an alias that shovels out to an ordered map and hash map on a couple of other maps we have, unify all of those interfaces, and then flip a switch and change everyone over, but it was too dangerous. We have too many hash maps. So here's a little story. I'm going to tell a little story. Once upon a time, there was a type called array slice at Google. It's a non-owning view of contiguous memory, and it is read-only. It has a constructor that takes an anything as long as it's a contiguous in memory implicitly, and it has an operator brackets that returns a read-only reference. Around the same time, there is also another type called mutable array slice. Mutable array slice is a view over contiguous memory, but it's writable. And it has a constructor that takes a pointer to anything. At Google, we have an idiom that mutable parameters are taken by pointer. And it has an operator brackets that gives a read or write reference. And it's not too hard to convince yourself that these are just two spellings of basically the same thing. These are the same type, but an array slice is basically just a mutable array slice of const t. These types are used, depending on how our tooling feels these days, it kind of chokes on it, anywhere between 50 to 100,000 times in Google's code base, almost always as function arguments. This is basically designed to be a function argument. You can pass a vector to it, you can pass an array to it, you can pass a whole bunch of stuff to a span. There's a proposal for something similar to rspan, although there are a decent amount of differences. We wanted to ship this, right? We want to take our internal idioms and export them when we need to. But we don't want to ship two types that are basically the same thing, except one says mutable in the name. That's not good design. So it fell upon me to figure out how to merge these into one type. And this is made much harder by the fact that they're taken as function arguments. So you can't rely on implicit conversion because you only get one of those at any one time. Span has to be an array slice exactly, but span also has to be a mutable array slice exactly. It needs to be able to wear both masks while we're making this migration. So there's kind of a tool for this that I tried. You could try doing this alias. For those who don't know conditional, stood conditional is like a ternary operator for types. It takes a compile time bool and two types. If the bool is true, it's the first type. If the bool is false, it's the second type. So this kind of accomplishes what we're looking for. It's unfortunate because, or it's nice that we don't have to rewrite any implementation. As it turns out, the implementation of span is a lot more complicated than it would seem. All of the implicit conversions make for a lot of very, very hairy and subtle sphenae. So we don't want to rewrite implementation as much as possible when we're doing this. What happens here? Anybody want to guess what this compiles? It's not a courageous crowd for answering yes or no questions. This does not compile, which is a little bit weird. Because looking at this, it's really intuitive to say, well, we're taking a span of int, and we're passing it to a thing that takes a span of t, so obviously t must be int, right? This is a very intuitive thing for us to say. But span is a dependent type. It depends, its type depends on its template parameter. So we see no matching function call to take span, and the first time I saw this error message, I was absolutely floored. I did not know about dependent types, and I sat back and just like, I have no idea. It's right there. It's right there. Like, it matches up. I don't get it. It's literally like it was this close. The function it was calling was literally right above it. Like the compiler, it's just do the thing. Come on. It couldn't infer template argument t, and this is what I was talking about with dependent types. The compiler, span looks like a template class, but it's not. It's a template alias, so we need another way to do this thing. So we are going to need to do a little bit of rewriting, but what we ended up with is something that's morally very similar to all of the other strategies I talked about in this talk. It turns out that for historical reasons, and because they're also very similar, mutable array slice and array slice had two implementation classes which dealt with the sphenae of those constructors that take everything, and then forwarded back to a central implementation class that held the pointer and the size and did all the actual logic of the class. So we can hide the dependent type inside here. And you can do this generally, as long as you have some way to discriminate at compile time what implementation you want dependent on your t. I could have switched between a million different array slices if we had a bunch all sitting around Google for whatever reason. Thankfully, we didn't. We only had two. But this works. This is totally fine. And this is exactly what we were doing before. Array slice and mutable array slice, they become aliases. The span is now our class, and we did exactly that. I spent a couple months just cleaning up the entire implementation. I think I ended up removing like over 100 lines of metaprogramming from the implementation, something crazy like that. It felt really good. And with all the caveats of our list of how to make owls sad before, this works. This is a way to migrate non-atomically all of our 100,000 array slices everywhere with the correct coupling between the old name and the new name, even though they will eventually change to be different things bit by bit. So this is my claim. Aliases, while nice to give meaning, maybe you don't want vector of character, maybe you want player list or something, I don't know, in your game engine. I claim that really aliases are a tool for gradual non-atomic refactoring. They create the correct coupling between two names such that you can move piece by piece, change your dependencies, do very, very large scale reorganizations of heavily dependent on code in a pretty reliable way, and the only things that break it are pretty reasonable to not ask user code to do. And also fairly easy to fix when you see that break after you've seen it before. They're in fact such a powerful tool for gradual non-atomic refactoring that just 3 months ago, this is September 2017 for the video, about 3 months ago, the Go team, another language at Google, who are very famously do not like to add features to their language. It's a very minimal language. They added type aliases only, to their language. And if you read their blog post about it, the expressly stated reason was, we needed a way to do large-scale code-based refactorings and reorganizations. We have fundamental dependency problems that we can't solve without these at the size of code base that the Go compiler now is. So this is really the hidden power of aliases. And that's how you can rename a type. Thank you very much. If anybody has any questions, I'd love to hear them. Hi there.
Hi. I'd like to know, there was a part where you showed the alias saying that old equal new, and you said that, okay, over here nothing interesting is happening. But I would have agreed if it was new equal old, but I'm looking if you have any guidance, because in the case where you're doing old equal new, you could have code which is using stuff like such as DLSym in order to look at symbols at runtime. And how could you, have you had any experience refactoring such cases where symbols are being found at runtime?
Yeah, so I don't. Google produces statically linked binaries, and if you actually look at our the project guidelines for Abseil, we talk about we don't particularly give any guarantees for dynamically loaded libraries for precisely this reason. You can't do it statically.
Okay, thank you.
Thanks for the question. Okay, if there are no other questions before people leave, this is my first talk at a major conference, so I really want to take a selfie with the audience. Oh, wait, do we have another question?
Yes.
Oh, perfect. No selfie yet.
I'm wondering if you've also had in refactoring cases where in order to make a very, very large scale refactoring, you would actually start and deconstruct the old type, like piece by piece. So like, let's say you make one of the various constructors disappear at some point so that you can slowly get rid of a very large amount of references to that.
Yeah, we do that all the time. Getting rid of a constructor, changing a name. Pretty, I think, really impressive one that we just finished recently was our internal version of string view, which we called string piece. Was it they had signed or unsigned? We had to switch from signed integers to unsigned integers in, I think, size and dot size. Yeah, which if anybody can think about like the difference in semantics between signed and unsigned integers is that's a scary thing to do. That's a very scary thing to do. You could introduce all kinds of undefined behavior. And we did. How long did we spend making that change?
Mark, how long did we spend? 9 months.
We spent 9 months making that change, little bit by little bit. Just literally we have other talks about it, tons of tiny changes that are run more or less automatically with some human change, using a lot of Clang tooling to actually generate that change. And it works really nicely. It makes these sorts of things like changing an integer from signed to unsigned on a heavily used library type like very doable and more or less straightforward.
So at some point you do get like kind of a situation where your whole type is actually just partial representation of your new type because you've stripped down some of the.
Well, so it depends what you're doing. We have also, so like, so for span, I actually changed the name first because that's like whether or not it compiles is kind of the important thing for span. It's really that constructor that I showed you that is like, if I did this FINE wrong in the constructor, I didn't even have test failures. We couldn't build the test system because it used span so much. So that was my test failures. So it really depends on just the particular engineering task at hand. Do you want to clean up the type first and then move it? Do you want to create your bridge and then clean it up later? Often you can do that at the same time. That's a nice thing about renaming first, is then while you're actually going through the code and renaming things, you can also start cleaning up the type at the same time. You can kind of parallelize the task.
Thank you.
Thank you.